Welcome back once again, my fellow mathematicians. We are ready to do some more division problems with our polynomials. This time we're going to be looking at a much simpler synthetic division process. So this is following up to your long division for your polynomials, and this should be recorded in your interactive notebook on page 35 as you're keeping up with your notes. So instead of using the long division process to divide these polynomials, we are going to use the synthetic, which is much more simplified method process for dividing these polynomials. So for this synthetic division, just like we did with long division, first your polynomials must be in standard form, and they must be in descending order of degree without any missing variables. So if we look at this, we have the highest degree as x to the fourth and then x to the third. But notice how this particular polynomial does not have an x squared term. So we will have to have a placeholder for that x squared term. But when we do synthetic division, the only thing that we need are the coefficients for each of the variables. No letters, no exponents. All we have is numbers. Much more simplified, much easier to follow synthetic division process. So only taking the coefficients, so I'm going to use the coefficient 3 to represent the x to the fourth power, and -1 representing x to the third. Remember that we must have the 0 placeholder for our x squared variable, and then we have 5 representing x and a -1 as our constant term. Now it says that we are going to be dividing this polynomial by x plus 2. However, when we do the synthetic division process, we actually are looking for the 0 of that divisor, or in other words, what is the value of x that would make this x plus 2 become 0? Well, that value would be a -2, just simply switch the sign. So then in my synthetic division process, I'm actually going to be using a -2 for my division. And when we put the box around the divisor in this case, rather than around the dividend of what we're being divided, we do a box around what we're dividing by. All right, so then all of synthetic division, again, simplified method, all of synthetic division takes place within 3 lines, and that's all that we need in this process. So the first number, we just simply bring that down. We're not going to change anything with it. It's going to stay exactly the same. But then this bottom row, rather than long division working our way from top down, we're actually going to work on synthetic division, works from the bottom up. So I'm going to take this bottom number 3 and I'm going to multiply that times that -2. So 3 times the -2 is -6. That's going to go directly below the next coefficient of -1. Then I'm going to be adding these two numbers together rather than subtracting them. So I'm going to add -1 plus a -6 is -7. And then the pattern continues. So then -7, multiply that by the divisor -2, gives me a positive 14 right here. Then I'm going to add 14 plus 0, just stays the same at 14. Again, multiply 14 times the -2, gives me a -28. -28 plus 5, so now I'm at a -23. -23 times -2 leaves me with a positive 46. Add that to an already -1, and now I have 45. And the 45, this last number there, again, always represents that remainder of what I have left over, remainder. Okay, so then your final product for your polynomial, or not product, but the quotient, after you have divided using the synthetic division process, you use these coefficients and then plug the variables back in. Because the original polynomial started with an x to the fourth, we're going to take one less than that because we have just divided by an x. So then our quotient would end up being 3x cubed minus 7x squared plus 14x minus 23. And then again, using our remainder as a fraction over this x plus 2, go back to the original divisor, x plus 2, because that's what we have left over after we have divided by x plus 2. And that's the synthetic division process. So let's look at one more. So now this time we're going to take 6x squared minus 5x minus 6 divided by x plus 3. Now in this case, first it has to be in standard form. Yep, everything's in standard form, and we cannot have anything that is missing. Do we need any placeholders for anything missing? We have x squared, we have x, and then we have a constant term, the negative 6. So no, nothing is missing, so then I can simply start with just the coefficients. So I have 6 representing the x squared, negative 5 for the x, and then negative 6 as my constant term. Then again, because I am dividing by x plus 3, when I multiply in synthetic division, I'm actually going to multiply dividing by negative 3. And then again, everything is going to take place right here within this 3 lines. So the first number, we're just going to bring it down, which is just 6. Then we're going to multiply. So 6 times the divisor of negative 3 is a negative 18. And then I am adding a negative 18 plus a negative 5 gives me a negative 23. Negative 23 times 3 ends up with a positive 69. 69 plus a negative 6 gives me a positive 63 left over, as that is my remainder yet again. So then for my final solution, or for my final quotient, taking 1 degree less than the original polynomial, this would be 6x minus 23 plus a 63 over x plus 3 as my final quotient. So then now we come to the remainder theorem, which basically just says that if I do synthetic division, the remainder that I have left is actually representing the value of the polynomial function at that given point A. So in the previous example, we were dividing by x plus 3. So when the value of x equals negative 3, the polynomial is equal to 63, because that was the remainder that we had once we did the synthetic division. So we can use synthetic division actually to evaluate the function themselves. So if I take this example of 2x to the third plus 5x squared minus x plus 7, and I'm going to evaluate it for the value of x equals 2. Now, yes, I can do the math, and I can take x equals 2, and everywhere I see x in this polynomial, plug in a 2, and that's going to give me my answer. But the really cool thing is that we can also do synthetic division, and that's what we're focusing on, so that's what we're going to do. So we're going to do synthetic division for this problem, and whatever we have left over for our remainder is actually the value of the function at that given value for x at 2. So we're going to do synthetic division. So we are going to just simply take the polynomial coefficients. So I'm going to take 2, 5, negative 1, 7, all of which none of them are missing anything, degree 3, degree 2, degree 1, and then degree 0. So I don't have any missing terms already in standard form, so just simply take the coefficients. And they already gave me the value of x as a positive 2, so I'm just going to use that. I'm not going from the factor to the x value, so I just simply take x as it is. So in my synthetic division process, I'm going to first bring down the first number. That's going to stay the same. So keep the 2. Then I'm going to multiply. 2 times 2 gives me 4. Add the 4 to the 5 is 9. 9 times 2 is 18. Plus a negative 1 is 17. 17 times 2 is 34. And then 34 plus 7 is 41. So that means that the value of the function when x equals 2 is 41. So in other words, I could say that the value of the polynomial when x equals 2 is equal to 41. So it actually represents a point on the coordinate plane of 2, 41. And again, yes, I can take the value of 2 and plug it into the polynomial. Everywhere there is an x, put a 2 instead, and then add, subtract, and multiply all of that. And once I get my final answer, the final answer will be 41. And that's a simple way to check to make sure that you did do that synthetic division correctly. So again, that is the synthetic division process. If you have questions, concerns, or issues, please feel free to stop by my classroom. I hope you have enjoyed, and see you next time.